James Stewart Modena, and I am a PhD DPhil student here at the University of Oxford in the chemistry department. And I'm going to be talking to you today about quantum dots, which were the winner of the 2023 Nobel Prize in Chemistry. So, here's how it works. We'll just start off with just a little bit about me. So I went to my local state secondary school from 2012 to 2017. Here are some of the GCSE options that I did. Spanish is in brackets because I took it a little bit earlier because I am Spanish. So it made sense for me to do that. And then I moved on to sixth form where I did A levels. So I did chemistry, maths, and history. I moved on to then the University of Nottingham, where I did an integrated master's course. That's why I spent 4 years there rather than a normal 3-year degree. But it means that at the end of it, I came out with a master's degree rather than a bachelor's degree in chemistry. So a couple of things that I did whilst at the University of Nottingham. So in my 3rd year, I had an undergraduate lab project on nanoparticle synthesis, which we'll come back to a little bit later. I did a summer research placement working on carbon dioxide electrochemistry, so trying to turn carbon dioxide into useful chemicals using electricity. And then I did my master's project on iron chemistry using a low coordinate iron species, which was very reactive for a reaction that involved carbon monoxide in order to turn that carbon monoxide into a red dye, which could potentially be useful, but was more sort of fundamentally interesting. And then, of course, I ended up at Oxford, which is how I'm now here today speaking to you. I'm actually at University College rather than Balliol College, but they very kindly let me speak to you today. So I was accepted onto what's called the OxICFM CDT. So a CDT is just a Centre for Doctoral Training. It just sort of simplifies a lot of the, or at least for me, it simplifies a lot of the funding to be able to do my research. And my research, I've put my research title there on the slide, but it's basically I'm looking at aluminium molecules that are bonded to other metals, say for example iron, and I'm seeing how those molecules will react with small molecules, so things like carbon dioxide, carbon monoxide, nitrogen, hydrogen, those sorts of things, to be potentially useful in the future. One thing that I haven't gone through yet is what OxICFM stands for, and that is the Oxford Inorganic Chemistry for Future Manufacturing. So future manufacturing, obviously we want our chemistry to be useful, we want it to be applicable so that it can go on and benefit people. But inorganic chemistry you might not have come across yet. You might not have sort of separated out. So I'll talk a little bit about what that means now. So chemistry can sometimes be separated into 3 main topics. So you've got your organic, your inorganic, and your physical chemistry. So organic chemistry is primarily around carbon-based compounds. So things like medicines, pharmaceuticals, those sorts of things would come under organic chemistry, maybe. Inorganic chemistry is primarily around non-carbon-based compounds, which, if you think about the periodic table, means that there's an awful lot that is classed as inorganic versus what's classed as organic. But these descriptions aren't really doing the full justice that it really deserves. Organic chemistry, you're interested in sort of the mechanism of how things are happening. You're interested in what those molecules, how to get to them. Whereas inorganic chemistry, you're interested in what the sort, for example, catalysts are doing, what are the metals doing. And then there's physical chemistry, which is the physics that are involved in these chemical properties and reactions. And so these sort of separated ideas can be useful. Sorry, I'll just put a laser pointer on. These sort of separated circles can be useful for teaching purposes, but when you actually get into research, into what you're specializing in, you'll very quickly end up in these sorts of middle sections here. So for example, my project, what I'm currently doing, I'd say right now, I'm sort of in this section here, because in order to make my metals bond to each other, my aluminium to my iron, my aluminium to whatever, I need to have sort of a carbon backbone around the metal, supporting it, holding it in place. And so really, my area is currently in here. Sometimes you could describe that as organometallic, but that's a topic for another day. I have some friends who I know operate on porphyrin molecules. So these are sort of large carbon-based cycles that have some interesting physical properties that you can trigger with light. And so that would sort of really sit in this area. But our topic today of quantum dots does sort of operate in this section over here. And so I'm primarily going to be talking to you about non-carbon elements and some of the physics behind why they do what they do and why they're useful. So quantum dots, what are they? Quantum dots are very small semiconductors. Okay, they are particles of semiconductors that have different colors depending on their size. And you might have already sort of seen quantum dots in the real world in QLED TVs. So these very small semiconductor particles, so they can conduct electricity. They have a small band gap if you've covered your physics. They exist on a nanometer scale, so they're very, very small. Times by 10 to the minus 9 meters is sort of the nanoscale. And the Nobel Prize website had this quite useful comparison, which a lot of the images from today are from the Nobel Prize website, if you want to go and do some reading on afterwards. And they compared, if you took the size of sort of a typical quantum dot and compared it to the size of a football, the ratio between them would be quite similar to the ratio between that football and the size of the Earth, our entire planet. So that sort of gives you an idea of scale of how small these particles really are. And chemistry at this very small scale can get a bit weird, which is why it's an interesting area of research. So you can see here we're not talking about individual molecules as such, but we are talking about things like proteins, viruses, that sort of scale. Depending on how far you've come in your science courses so far, you might have covered a little bit on Buckminster fullerene, which is a C60 molecule, which is a nanomaterial. You've got quantum dots, which we're talking about today. You've got metal nanoparticles, which I'm going to talk a little bit about here. Metal nanoparticles, for example, titanium dioxide, are used in sun cream. That's the part of some white sun creams that protect you from harmful UV radiation that comes down in the sunlight. So the UVB, I believe. Slightly more on the academic side, I worked during my summer placement on CO2 electroreduction. I worked in the nanocarbon group in Nottingham. And the idea was basically to have this sort of carbon nanotube and to fit copper into and on the outside of it, so to sort of decorate the carbon nanotube with it. And that would give us nice sites in order to do our electrochemistry on the carbon nanotube. So how do you measure things that are that small? Obviously, you can't just take out a ruler. So one of the main techniques is to use electron microscopy. So it sort of has a similar idea behind it to a light microscope that you might have in your science classrooms. I'm not sure if you're currently sat in a science classroom, you might have one in there with you. But instead of using a light source in order to illuminate and not increase the size, but increase the image size, you use a source of electrons. So you fire an electron beam at your sample. Those electrons will then either be absorbed or scattered and transmitted. And by using detectors around your sample, you can build up little black and white images like you can see here, where the black, sort of the darker areas, are where electrons aren't, so they've been deviated away from here, and that's where a lot of your product will be. And so you can build up these sorts of images, which you can then interpret as, okay, well, we've got this area here, which is slightly darker, so that's probably the inside of our carbon nanotube. Pardon me. And then you've got this really dark aspect here, so that's probably something that's inside of our carbon nanotube. This area is all sort of baseline, this is all sort of normal, and so that's just space around our nanotubes. And these electron microscopy techniques can be used to measure things like the size, the shape, and a couple of other properties of various nanomaterials. But the thing about quantum dots that's really interesting is their color. And color at the nanoscale can be a little bit weird. So I'm going to put up a little poll for you now, which I'm launching in the chat now. What element do you think these are? So this here is a picture I took during my third year undergraduate lab course. So while I was making nanoparticles. And so, sorry. Yeah, this is in a round bottom flask. We have nanoparticles that are just in solution. What element do you think they're made out of? Give you a little bit of time for some of your guesses to come in. Looking at the current results, carbon is just nicking up. There's a couple of people who voted for iron is also iron and cobalt. Iron and carbon are our favorites so far. A couple of votes for gold, a couple for phosphorus and cobalt as well. Okay. Interesting. Going to close this poll now. And to give you the answer, I think some of you may know, because this is in fact gold. I know, I was describing this to Jack a little bit earlier and he was also surprised. But when you shrink gold down to really, really small, it turns into a red color rather than the sort of shiny yellow gold color that we use so often, that sort of saying that something is a gold color is just a normal everyday word. And in fact, we've sort of been doing this for a very long time. So this is the Lycurgus cup. It's a Roman artifact in the British Museum, and its glass is actually infused with both gold and silver metal nanoparticles. So the reflected light that's sort of green is because of the silver nanoparticles, whereas the red color comes from the gold ones. So we'll just let this play out now. You can sort of see that depending from where it's lit, you will see a different color. Some of it is more sort of green silvery, which is to do with the silver, and then that red is from the gold that's just present in the glass. Some of the research on this that's gone into this artifact would sort of lead people to believe that these are just sort of trace impurities that they didn't necessarily mean to put into the glass as they have done. But it's still nonetheless quite interesting, quite cool that we've been using nanoparticles for color for quite a while, and it's now recently won a Nobel Prize. So, quantum dots. What are they made out of? So, unlike the nanoparticles that I showed you earlier that were purely either gold or purely either silver, quantum dots are typically made using a binary system. So they're made of two elements. Some common examples in sort of the literature and where the inspiration behind the prize include cadmium selenide, so cadmium and selenium, cadmium sulfide, so cadmium and sulfur, lead selenide, and indium arsenide, which is indium and arsenic. Now, you may realize that some of these elements are toxic. So you might have heard of lead poisoning. Arsenic is also fairly toxic. And so how old is the cup? The cup is from the Roman times. I believe it was 300 AD, I believe. Sorry, I just noted that question in the chat. Where was I? Okay, yes. So you might know that some of these elements have sort of toxicity concerns around them. You don't need to worry about those in your quantum dot TVs, in your QLED TVs, if you are lucky enough to have one, because most quantum dots are held in a shell of an inert material. So you have a quantum dot, and then around that you have another material. Usually it's some sort of zinc sulfide. What this does is that it prevents the quantum dot from leaching out, but it also prevents the quantum dots from agglomerating together and then becoming bigger, which is important because their size has an impact on what color they are. I also just wanted to attach a little thing here. A couple of my friends that I know, some people that I know, are doing research into quantum dots in order to try and use different elements that are intrinsically safer. So there's still some work going on in this area, but it has won a Nobel Prize. So how do quantum dots actually work? So all of these quantum dots here are held in solution, but they are all made of the exact same chemical. Okay, I believe this picture in particular is all cadmium sulfide, but you can see that they cover the entire visible spectrum, almost going from blue to red. And all of these chemicals, all of these particles are the same color. All of these particles are the same elements, but they show different colors. The reason why is because they all absorb in visible light, but then depending on the size of those particles, they will then emit out different colors. Those different colors that are emitted, those what reach our eyes, and therefore that's why we see it as those particular colors. In order to explain exactly why, I am going to need to cover some fundamentals of bonding that go a little bit beyond GCSE and technically a little bit above A level, but just trust me, stay with me, we'll get through this. So right now, you're probably familiar or comfortable with the sort of, sorry, I've just seen this question. So are the particles in each of these colors varying in size? Exactly right, yes. Yes, these are varying in size, going from smallest all the way around to the biggest. I hope that answers your question. So you're all probably familiar with this shell model of electrons and atoms. So you have your nucleus in the middle, which is where you have your protons and your neutrons, and then you have shells of electrons around it. Pardon me. Shells of electrons, once you move on from GCSE, would prefer to talk about electrons as being in different orbitals. And one of the main reasons why we like to talk about orbitals rather than shells is because it gives us sort of 3D space to work with. It gives us what direction those electrons could be pointing in. And the reason for this is because these different orbitals have different shapes. So the s orbital is just a sphere, okay? So, but the p orbitals, you have three different ones. They sort of sometimes described like dumbbell shaped, but I prefer to think of it as you've got two balloons and you're sort of pinching them together in the middle. So you've got two sort of big lobes, and you can have these lobes pointing in either the x direction, the y direction, or the z direction. And that gives you different geometries you can access. And so we typically would move the electrons over into these orbitals. When we're working with orbitals, we can also then help to describe your covalent bonding. So right now, you're probably familiar with describing covalent bonding as sharing of electrons between two atoms. So for example, using your dot and cross diagrams is probably what you're familiar with. Once you move into orbitals, you start to think about the overlap of them. So you can take these two orbitals, put them together, and they'll overlap in order to form two new molecular orbitals. Okay? So you start out with, once they come together, you get a bonding molecular orbital, which is where you have these two electrons that are shared in space between these two different nuclei. Sorry, I just need to make sure the chat comes back up. There we go. So yeah, you have this area of space that is associated with where the electrons can be shared between them. But when these atomic orbitals also come together, you also get an antibonding molecular orbital. Now, this is usually unfilled, but if you put electrons into these spaces, that will then break this bond here. Now, the reason why I wanted to talk to you about these is, as I mentioned, the forming and the filling of the bonding molecular orbital give you your covalent bond. As you can see here, they're shared between the two nuclei. It is also, this bonding orbital is also lower in energy than the individual orbitals. And that's quite important. And that's one of the reasons why you may say that bond making is energy releasing. It's an exothermic process because you're taking the electron from this energy level and you're going down in energy. So that energy has to release in some sort of way. You can also notice that the antibonding orbitals are higher in energy. And this is also why bond breaking is energy. You require energy. It's energy using its endothermic. So the energy values of each of these things, so these sorts of energy states here, can be described as quantized. And this sort of word quantized is where quantum mechanics comes from. It basically means that they have specific values that they are allowed to be. So it can be 1 or 2 or 3, but they can't be like 2.5. There's an easy way to visualize this in a second. But this is a key concept that if you do have questions, please do ask them. So in a single molecule, these different orbital overlaps create different energy levels where the electrons can be. So you sort of have these couple of bonding interactions here, which would be filled with electrons, and you have a series of anti-bonding orbitals, which are empty. And so I tend to think about this sort of a bit like a ladder. You can put your feet in each one of these steps, but you can't just sort of have your feet swinging in the middle and still be stable. In a bulk material, you might have come across this sort of structure of bonding, this sort of band structure, which is covered in your GCSE course in your physics. So in a bulk material, you have so many overlaps of these different energies, of these different orbitals, that they effectively become sort of continuous. So the way I think about this is sort of like you have a ladder versus a ramp. So no matter how small the sort of step on the ramp is, your foot can just lean straight down on top of it. So it's a smooth way up. Whereas in this sort of molecular structure, it's more like a ladder. You can only have your feet at a specific level in order to climb upwards. I hope that makes sense. Why this matters in terms of quantum dots is that quantum dots are in an in-between between the individual sort of ladder sort of idea of electron energies and the sort of band structure that we have in our bulk solid material. And that means that one of the things about quantum dots is as you make the quantum dot bigger, you add more atoms to it, you add more orbitals, and so the energy gap eventually shrinks between your filled state and your empty states. which means that when quantum dots absorb light, you take an electron from the highest occupied orbital that you have. So in this case, this level here, you shine visible light, and these electrons will be excited up into an empty site, so into this sort of antibonding orbital or conduction band, if you want to think about it in terms of bands you have. Yeah. These electrons will then relax back down to the lowest state that they can, usually by vibrating. So by vibrating and moving around, the electrons can get down to the lowest energy state that they can. Unfortunately, to relax back down to their original levels, which are here, here, and here, they have to overcome a big drop. And this big drop you can't access just by vibrating. The gap is too big in energy. But they can overcome this gap by releasing a photon. Okay, so you're probably aware photons are the sort of particle form of light that you know of. And so what happens is this electron will relax down to its original state, releasing a photon. And the photon will have an energy that matches this gap here. So a smaller gap will release an energy, will release a photon with lower energy. That lower energy will correspond to a longer wavelength, and the longer wavelength of light is red. And so the larger the quantum dots will appear red because they have a smaller gap. And as you sort of go over this series, changing the size, getting smaller and smaller, this gap between the lowest state and between the lowest unoccupied state and the highest occupied state, this gap gets bigger, which means the photon energy release gets bigger, which means that the wavelength of light gets shorter. And this is what gives you your range of colors. I hope that makes sense for everybody in the chat. Just checking that there aren't any questions. No, fantastic. So, how are the quantum dots made? So one of the biggest challenges with making nanoparticles is controlling their size reproducibly. Reproducibility is very important in our science, and especially when you want to make things industrially relevant, because you don't want to be sort of making weird batches, some of which work, some of which don't. You want things to be reproducible in science. So Lungi-Bawendi developed a method of what we now refer to as hot injection, followed by some size-dependent purification in order to get the size of quantum dot that he wanted. Pardon me. So we have this image here, again, also taken from the Nobel Prize website. So Bawendi took his substances that could form his cadmium selenide quantum dots, and he injected them into a hot solvent. And one of the things is that the volume of his reactants that he injected in was enough to saturate the solvent around the needle. What I mean by that is that around the needle, there was so much of the cadmium selenide there that it had no choice but to come out of solution and exist as crystals around the needle. I'm trying to think of an analogy that would work for this. Think about it if like you were making a cup of coffee, okay? If you're making a cup of coffee and you have like the coffee grounds that you put into your mug, and then you pour just like a tiny bit of water onto those coffee grounds, just the smallest bit you can, and you stir it. No matter how much you stir it, you're probably not going to get all of the coffee grounds dissolved up into that water, because the water has taken up as much of the coffee as it can, and it just cannot take any more, and so some of it is just left as a solid. It's a similar thing in this situation. You've just got so much cadmium selenide around the needle that you just can't fit any more in solution, and so some of it just has to come out as crystals. One of the issues that he came across, though, is that once you injected something cold into something hot, the temperature dropped. And so that would actually stop the crystals from continuing to form and continue to grow. So what they did was quite simply just increase the temperature again, probably not with a Bunsen burner or a flame. We tend to use hot plates that are a little bit more controllable now. And so by heating it back up again, that allows the particles that are still in the solvent to move around more easily to combine with the crystals, and therefore allows the crystals to grow and become larger. What was the solvent? The solvent in this case, I believe, was a coordinating solvent. I'm struggling to remember exactly which, but it was a coordinating solvent, so either diethyl ether, I'm not sure if you're aware of ethers, they're oxygen bound to two carbons that's bonded on each side to a carbon. So diethyl ether has got sort of an ethyl group, so a CH2, CH3 bonded to its oxygen on both sides, or it was in THF, which is similar to diethyl ether, but it's cyclic. That's a very good question. Thank you. And so by controlling the amount of time that these were heated for, you could control how they were grown in a controlled manner. So, as you can see, this is what the Nobel Prize website said about Mongiva Wendy, is that he managed to produce almost perfect quantum dots with specific sizes and smooth surfaces, which was necessary for them to be used in modern day applications like QLED TVs. And as the method was easy to use, it became revolutionary. I do also want to highlight Louis Brew and Alexei Ekimov for their contributions. So Louis Brew's contribution really came through in 1983, and he was the one who sort of showed some of the size-dependent quantum effects. So by that I mean the larger, pardon me, I mean that the larger quantum dots showed the shifting over towards the red color. He showed that those happened to particles that were floating freely in a fluid. So it says here, he noticed that smaller particles absorb light that shift towards the blue compared to the larger particles. But actually, in reading up on sort of his work, his notation was actually found by sort of just looking at an old sample and noticing that its color had changed. And the reason for that was over time, the crystals, the nanoparticles kept growing. And that's what caused, obviously, as the nanoparticles grew, the color changed, it redshifted. And so that's what he realized was going on. Alexei Ekimov, I should note, these quotes are both taken from the Nobel Prize website. I'm not entirely sure why his name, the spelling of his name has changed ever so slightly, but it has. And so I'm assuming this is some sort of translation error. It is just the same person, I promise you. And he created size-dependent quantum effects in colored glass. So in his case, it was in copper chloride nanoparticles. And again, he sort of demonstrated particle size affecting the color of the glass via quantum effects. I realize now I've gone through this all very quickly. I've spoken quite quickly. So I want to thank you for listening and then invite you to ask any questions. Please do if I've went over something a little bit too quickly for. Thank you for listening, and I hope that you have questions. Are they only receiving the Nobel Prize now because their research made applications of quantum dots possible recently, or did it just take a while for their discovery to be recognized? So one of the things with Nobel Prizes in particular is that they take a bit of time before sort of scientific progress takes some time before you can really realize how impactful something is. So it's a bit of both of the options that you presented there. So the fact that quantum dots are now being used in some consumer goods is definitely one of the reasons why they won the Nobel Prize. Historically, there was a bit of a challenge in producing blue LEDs in order to produce white light, and so anything that can make blue LEDs is quite important, just based on historically. But you're also right in that it does take time for discoveries to become as important as they are. Okay, this is a reality of working in science. Is that sometimes something that you discover may not be realized to be a big deal until many years later when somebody else picks it up again. And so yeah, you'll notice that a lot of these Nobel Prizes tend to be for older work that is then re-examined. What are the main applications of this theory? If you're talking about quantum dots, the main applications are in LEDs, and that can be particularly useful in the mainstream for TVs. If we're looking more towards a sort of a scientific point of view, one of the things that's very good about quantum dots is they give out a very specific wavelength of light, in that they have what we call a narrow half-width at full, not half-width at full maximum. So the wavelength of light that they give out is very sort of sharp in a UV visible spectrum. And that's quite useful for things like photochemistry, where you want to excite a molecule with a specific wavelength of light in order to produce a specific effect. So in order to excite a molecule to a particular state whereby it can then react on further. I hope that answers your question about applications of this theory. If you're talking about the sort of fundamentals of bonding that I mentioned earlier, those fundamentals of bonding will apply pretty much everywhere throughout chemistry. It's molecular orbitals and sort of orbitals in general. That sort of theory really underpins a lot of reactivity, a lot of geometry that we see in our molecules. So I hope that answers your question. Did quantum dots allow for color TV, or was it possible before? Color TV was possible before quantum dots, but quantum dots are sort of a next step. So you might see quantum dots advertised as having purer color, is one of the things that I think it's Samsung describes their QLED TVs as being. And the reason for that is, again, that narrow half width, full width at half maximum. That's full width at half maximum. So yeah, that's one of the selling points. The picture on the screen, the light that they give off, how long does this last, or do they continuously give off colored light? So if they're lit up by just sort of normal lighting, yeah, they'll be like that basically forever, because they'll continue taking in and then emitting the colors. In terms of this picture, I'm not 100% sure on how they took it. I don't believe that they just continuously emit the colored light. Are quantum dots magnetic? My initial thought would be no, but some of them could be if you manage to get a material that. So I don't believe that the cadmium selenide or the cadmium sulfide ones. Yeah. So in general, quantum dots themselves aren't all magnetic, but some of them, I imagine, could be. Yes. Are quantum dots nanomaterials? Yes. Quantum dots are, by definition, nanomaterials, because these sorts of effects, whereby shifting the size shifts their color, only apply to when they are on the nanoscale. So I think some of the largest quantum dots will be sort of up to around 100 nanometers, whereas some of the smaller ones may be on the sort of tens of nanometer scale. Why did I choose to do the talk about quantum dots? I chose to do the talk about quantum dots because they were the Nobel Prize winner last year, and I thought that that could be an idea to show you some very sort of well-regarded chemistry. It also gives me a little bit of a break from some of my own work, which is, it can be quite nice at times to look around at what else is happening in the field of chemistry. My work is more sort of molecular systems, as I mentioned at the start, organometallics and the like. If you continue on, I'll give you a little bit of a plug here, Jack. If you continue on with these sorts of Balliol outreach, I do a talk on the Balliol Frontiers program. I gave a talk on there about organometallics, which is more my own area of expertise. So if you stick on with this, you might see me at some point. Yeah. Are quantum dots hazardous, and if so, why? So there hasn't been any proof that quantum dots are particularly hazardous. One of the things with nanomaterial, just nanomaterials in general, is that because of their size being so similar to, I'm just going to go back and show you this slide here. So because nanomaterials are so close in size to, just bring it back up my laser pointer, up to biological, because nanomaterials are around biological in size, the interactions between those haven't been fully understood yet. So there are some concerns that nanomaterials could be dangerous if they get into your bodies, because they could sort of block off aspects of your body's function. In terms of sort of inherent danger, it's mostly to do with some of the elements that some of the quantum dots are made from. Say, for example, lead or arsenic are known to can cause poisoning. And so there are concerns just in general about using those, even if they are sort of quite contained within the sort of zinc sulfide shells. So it's one of the things that chemists would like to do is just in general shift to things that are more likely to be safe. One of the things that you'll probably learn about is CFCs, chlorofluorocarbons, and the effect that that had on the ozone layer. And that was really dangerous, and because the CFCs destroyed the ozone, which created the ozone hole around the South Pole. And so one of the things as chemists is we want to make sure that what we provide to people is safe. And so we don't really want to wait until you can have sort of full toxicological testing. Obviously, it's important, but ideally we want to make things as safe as possible. Any other day-to-day applications where quantum dots could be used? Currently, they're primarily being used for their lighting capabilities. So that's the primary industry that they're currently in LEDs. But in the future, it's possible that they become more energy efficient. And if they become more energy efficient, you could see them start to be used in, for example, light bulbs, perhaps. Are there any applications of the research you're currently doing now? So my research is on aluminium bimetallics. So, pardon me. So I'm going to be looking at, I should say, this is about my 8th week being in a lab, so I haven't really got many results yet. But the general idea behind my topic is to try and put as much electron density as I can onto a metal, so that that metal can then go on and react with something like carbon dioxide, let's say, is the easy example. Because if you can convert carbon dioxide into a useful chemical, that would be really useful in dealing with the global warming crisis that we're currently handling. Frontier Year 12 program. Thank you, Jack, for giving the official plug for that. What's a dendrimer? So a dendrimer, you might have noticed this here. So a dendrimer is sort of like a large branching out structure, usually involving sort of like think of it a bit like the top of a tree with all that sort of foliage out. It all comes from different branches, and then you have the leaves around it, which sort of create the sort of full picture. The reason why you'd use dendrimers, for example, is you could attach those onto molecules of interest and then allow sort of change some of the solubility around them, maybe. So one example that I'm trying to remember from my year 3 undergrad lectures, so about 2 years ago now, so bear with me here. If you can attach sort of dendrimers onto a biologically active medicine, you might be able to improve how well it travels through the body. Because a lot of the things that, for example, inorganic things that I work with don't really mix well with water. And inside of our bodies, there's a lot of water. So if you can put a dendrimer onto your molecule and sort of have that sort of protection come around it, with, for example, carboxylic acid groups or alcohol groups that would just improve the solubility in water, you can then apply that medicine more easily into the body and have it accepted. I hope that explains what a dendrimer is. Any other questions?
I have one last one if you've got time, James.
Sure.
Going back to when you were younger and you were in school, did you know early on that you were going to pursue a career in chemistry, or did you kind of find out as you went through sixth form and stuff?
Not at all. So this is something that I would really recommend to, well, your year 10s, I believe, here today, year 10s.
Yeah, that's right.
So you can see here that what I went on to do was I did at sixth form chemistry, maths, and history. And the reason why I did this was, first of all, chemistry was something that just sort of stuck in my brain quite easily. I really sort of got on well with the idea of how molecules reacted with each other, and that sort of just made sense in my mind. And it was just something that I found quite cool and quite interesting, and something that I wanted to know more about. So kept going on with that. And so that's something that I'd really recommend to you as year 10s, is just follow what's interesting. It's just go with what seems to work with your brain. We're all a bit different, and that's good. And there will be some things that you are naturally better at. And I encourage you to follow what you feel you're best at. So I didn't know that I was going to go down sort of the chemistry angle. I picked chemistry as my science because that's the one I found most interesting. I was quite good at maths, so I decided, okay, I'll stick with this. But then I found history quite interesting just as a topic in general. So I thought, yeah, I'll take history. But during my GCSEs, I took drama, which is something that I massively enjoyed. I massively enjoyed acting as a kid, and I enjoyed performing. And so it's just something that I found interesting, and I would encourage you to follow what's interesting, because when you do that, you're less likely to get bored. And in my opinion, getting bored is the thing that will sap you of all of your energy the quickest when you're going through something. How am I doing today? I'm doing very well. Thank you very much for asking. I was running a reaction today, actually, that was I'm hoping to get back to, and I'm hoping has worked. So fingers crossed. I go back and my yellow solution has turned white. So
I think there's a couple of questions about quantum mechanics and stuff that I don't think we've yet covered.
do quantum mechanics apply to quantum dots? Okay, right. Quantum mechanics do. The thing about quantum mechanics is that it's quite a broad sort of topic, if you will. So when I say that energy levels are quantized, quantized is specifically referring to quantum. Okay, so anything that has quantum in it specifies that it has specific levels that it can be. So it can be, as I showed you here, I just to escape and go back down to here. So do quantum mechanics apply to quantum dots? Yes. One of the things about it is that obviously as they are quantum in nature, they have a specific energy levels here and here. Those specific values are what determine something to be quantum. Are they dangerous? Not inherently. We don't have evidence that they are dangerous. We have evidence to show that they are safe for now. But it's something that as chemists we should be vigilant around it, just to try and make sure that things are safe. Just as a general point is that we want our things, our chemicals, our chemistry to be safe for everybody. And so it's something that we are constantly monitoring. And I think that that's quite a good thing, actually, to constantly monitor and check yourself to make sure that what we're doing as chemists is beneficial for people. I hope I've answered your questions.
I think, yeah, pretty comprehensively. That was it's such a fascinating topic, and I think we could talk about it for a long time, couldn't we? Especially if we go down in the quantum mechanics route. That's something that people just talk about for years.
Yes, this is one of the reasons why I tried to steer around that question a little bit. So I do apologize, but that is a question on how I use quantum for the applications that I need to. It's one of the aspects of physics that will come into chemistry, but we use it as a tool, whereas other disciplines of science, so for example, some biologists, some pharmacists that I knew would have to take chemistry modules, and they would be like, oh, I have to use chemistry as a tool, whereas I find it interesting as a fundamental. And both are valid.
Brilliant. Well, thank you so much, James. I think we'll end things here because I think we have run out of questions. But thank you so much for asking those questions. It's really appreciate the people listening and taking an interest and clearly are on board and genuinely invested, because some of the questions were really, really insightful. So that's it for today. I hope you are looking forward to next week, which will be your final discovery session, and that will be on psychology. So we look forward to seeing you all again next week. And that's it from us. Thanks again, James. Bye, everybody.
Thank you very much.
Thanks for coming.